In this video, we expand our notion of the derivative at a point to the derivative as a function that itself can be graphed. Number one, let f of x equal x to the fourth power. Part A says to use the limit definition of the derivative to find f prime of x. We're not allowing ourselves to use the power rule yet. Then in parts B and C, you can see we're going to make graphs and we're going to make approximations. Let's do part A first. We need the limit definition of the derivative. F prime of x, by definition, is the limit as h goes to 0 of a difference quotient written f of x plus h minus f of x all divided by h. This is ultimately a limit of slopes of secant lines, which by definition is the slope of the so-called tangent line to the graph at a particular number x. But the thing that's new in this video is that we can allow x to be anything. In the previous video, we picked specific numbers for x. Now we're letting x be anything. But we do the computations in the exact same kind of way. We're plugging, first of all, x plus h into f of x, meaning replace x with x plus h. In this case, we need to do x plus h quantity to the fourth power, which sounds kind of scary, but take a breath, we can do it. Then minus f of x, which is x to the fourth, all divided by h. Again, as I mentioned in the last video, you could use the binomial theorem to expand this, and if you know it based on Pascal's triangle, go ahead and do that. I'm not assuming that you know how to use the binomial theorem, so I'm going to go ahead and multiply this out by first doing x plus h quantity squared times itself. And when I square it, I can use FOIL, and that will be something that you will probably be familiar with. So I'm now going to multiply x plus h times itself twice, and then multiply the results. So x plus h times x plus h, I could write that over here and imagine doing FOIL, F-O-I-L, first times first, outside times outside, inside times inside, and last times last. Don't forget to carry along the limit sign as you go. First times first is x squared. Outside times outside is x times h. Inside times inside is x times h. So those two terms give you 2xh. And then last times last is h squared. But I do it again. I have another x plus h quantity squared, so I get that exact same expression, that exact same trinomial again. And I will have to multiply these trinomials then. Don't forget to subtract x to the fourth, and then divide by h. What's going to happen here ultimately, if you don't make a mistake, is that any terms that don't involve an h in the numerator will be canceled, and we'll be able to factor out an h out of the numerator and divide it out with the 1 on the bottom, and then ultimately plug in 0. That's always what happens in these types of problems, fairly simple problems with power functions, if you don't make mistakes. So now go ahead and keep going. We need to expand this out. I'll start with the x squared term there and multiply it times every term. That'll give me x squared times x squared is x to the fourth. X squared times 2xh is plus 2x cubed h. And then x squared times h squared is plus x squared times h squared. And then go to the second term on the left, 2xh, and multiply it times every term. 2xh times x squared is 2x cubed h. 2xh times 2xh is plus 4x squared h squared. And then 2xh times h squared is plus 2xh cubed. Try to write a little smaller here as I'm running out of room. Now go to the last term here. H squared times every term. H squared times x squared is, I'll write it as x squared times h squared. H squared times 2xh is 2xh cubed. And then h squared times h squared is h to the fourth. Don't forget to subtract x to the fourth, all divided by h. I could cancel the x to the fourth right away, but I think I'm going to simplify this expression here first, just to emphasize what you would get if you used Pascal's triangle. Limit as h goes to 0 of combine like powers of x. We've got just one term that involves x to the fourth. We've got two terms here and here that involve x cubed. Combine them, you get 4x cubed h. We've got three terms that involve x squared times h squared. Here, here, and here. So we'll get, when we combine, look at the coefficients 1, 4, and 1, we'll get plus 6x squared h squared. The terms that involve just x to the first power are, where are they here? This one here and this one here. Combine those and get plus 4x h cubed, and there's only one term involving x to the 0 power, which is this h to the 4th power. And the coefficients that you see, well, there's a 1 there implied. 1, 4, 6, 4, 1 come from a row of Pascal's triangle. Now I'll go ahead and cancel the x to the 4th powers on top. What's left, this term, this term, this term, and this term all have a factor of h that can be factored out like this. And then we are going to divide that h out with the 1 on the bottom. Be careful here not to make a mistake. Can't plug in h equals 0 yet because we'd be dividing by 0, but once we divide it out, then we're left with the limit of this thing as h goes to 0, and as a function of h for any fixed x, it is continuous. And I can therefore finally evaluate the limit by plugging in h equals 0. And for extra emphasis, I'll get 4x cubed plus 0 plus 0 plus 0 is 4x cubed for the answer. And if you know the power rule, you knew that had to be the answer ahead of time. This step right here, going from here to here, is very subtle. I've mentioned this in previous videos. It's based on the fact that the limit doesn't actually depend on what happens to the function at h equals 0. This function right here is a function of h. Think of x as fixed. Is not defined at h equals 0. It can't be continuous there. But it equals this expression as long as h is non-zero. So if this expression has a limit as h goes to 0, this one will too, and they'll be the same. Because of that, and because this is a continuous function of h, the graph of this as a function of h would actually be continuous everywhere except h equals 0, but it would have just a point missing, a hole in the graph at h equals 0. But this function is continuous at h equals 0. It fills in the hole. And we ultimately plug in h equals 0 into that one to evaluate the limit because it's continuous there. Some real subtleties going on there. All right, that's part B, or part A, excuse me, and that could be found with the power rule if you know it, but I'm not assuming you know the power rule. Part B, sketch graphs of f of x and f prime of x and explain the relationship between the graphs. Of course, you could use technology to make those graphs, but let's try to do it without technology. It should be something you should be able to do just by thinking about it. So f of x here is x to the 4th. F prime of x is 4x cubed. I mean, yes, you could plot points. I'm not going to bother plotting points, so I'm not going to make a super careful graph. I'm going to make more careful graphs on problems to come in this video. So here's the x-axis. I'm plugging in different values of x. These are both power functions. This is a power function with an even power there, a positive even power. It's got to have n behavior that goes up to infinity, plus infinity, in either direction like this. And because it's just a plain power function and not a polynomial with more terms, its behavior will be fairly simple. It's got to look kind of like a parabola going down like this and being concave up. However, there is a subtlety here that I think is worth trying to pay attention to. When you plug in numbers between -1 and 1 into this function, like imagine plugging in, say, 0.5 or something, you'd be doing 0.5 to the 4th power, 1/2 to the 4th power, which is 1/16, which is pretty small. The output of this function gets pretty close to 0 pretty rapidly as x goes to 0, and that's a pretty vague explanation. But what that means for the graph is fairly flat, you might say, near 0, more flat than a parabola technically is. You know, it's basically indistinguishable from the x-axis when you're really close to 0. And that is a subtlety worth paying attention to. So this is f of x equals x to the 4th. I'm not giving a scale here, other than to say this is just, when x is close to 0. And then the derivative, 4x cubed, that's a power function with a positive coefficient, odd positive power. Its end behavior is off to minus infinity as x goes to minus infinity, and plus infinity as x goes to plus infinity. It's fairly close to 0 as well when x is close to 0, though less so, you might say. So the graph probably looks about like this at first when x is positive. Probably above the graph of x to the 4th. It's close to 0, but not quite as close to 0 as x to the 4th is. At some point, though, because x to the 4th has a higher power, it's going to grow faster. So at some point, the derivative graph is going to be more like, is going to be below the graph of the original function. F prime of x equals 4x cubed. And a similar kind of thing, this is going to be an odd function. The red graph is an even function. It's got symmetry with respect to the vertical axis. The green graph here is an odd function. It's got origin symmetry. So the graph over here is going to look like this. As far as explaining, it's probably, I need to make it a little closer to 0 there, near 0. As far as explaining the relationship between these graphs, the derivative graph at any value of x tells you the slope of the original function's graph. So you can see in the red graph here, the slopes are very close to 0 when x is close to 0, and that means the derivative output as a function has to be close to 0. The slopes get more and more positive over here, so the derivative function telling you those slopes of tangent lines to the graph of f. You know, for example, right here, whatever the slope of that line is the value of the green graph there. Getting more and more positive. The red graph is concave up. The derivative graph has to be increasing. Over here, the slope of the red graph is negative. Tangent lines have negative slopes, so the derivative has to have negative values, and they get closer and closer to 0 as you move toward 0. Part C says to note that f of 2 is 2 to the 4th is 16, and f of 2.1 with your calculator, you can check this, 2.1 to the 4th is 19.4481. The directions say to use f prime of x to give a linear approximation to f of 2.1. And why is the approximate value too small? I'm previewing what you're going to find. Let's answer that last question right away, actually. The derivative, let's pretend, let's see, where is 2 here? I guess 2 to the 4th would be 16. 2 cubed times 4 would be 32. The derivative function is going to be higher than the original function when x is 2, so we could pretend 2 is maybe right about there. We're going to be using the tangent line to approximate the red graph there, near 2, in other words, when we plug in 2.1 in particular. And you can see, because that tangent line is below the red graph of the original function, it's going to underestimate it. The approximation is going to be too small. That's the answer to the question as to why the approximate value is too small. As far as approximating f of 2.1, I emphasized this in the last video. You use what's called a linear approximation. I sometimes write that as L of 2.1, where L of x is the formula for the function whose graph is the tangent line to the graph of f at the given point. And the formula for that is going to be f of 2 plus f prime of 2 times x minus 2, where I'm going to plug in 2.1 in place of x. L of x is f of 2 plus f prime of 2 times x minus 2. And I'm plugging in x equals 2.1 there. So f of 2 is 2 to the 4th. F prime of 2 is 4 times 2 cubed. This is 16. This is 32. 2.1 minus 2 is 0.1. So we end up with 16 plus 32 times 0.1 is 3.2. So we get 19.2 as our linear approximation to the value of f of 2.1, in other words, 2.1 to the 4th power. And yes, 19.2 is too small. There is the exact value for f of 2.1. Number 2 is kind of a fun qualitative physics problem about derivatives. A vehicle is moving along a straight road, and it's got distance f of t from its starting point at time t. No units are given. Of course, you could give units. The problem says match the description. There are 3 descriptions, A, B, and C, with the graph of f prime of t. In each case, there are 3 graphs, 1, 2, and 3. Okay? Assume the scales and the vertical axes are all the same. Description A. A bus is on a popular route, or route if you prefer, with no traffic. Popular route with no traffic. Okay, so it's whenever the bus is cruising, it can go a pretty steady speed, but then of course the bus is going to stop every so often and pick up people. It's got to slow down to a stop. The derivative is the velocity, or since this is one directional motion, you could think of it as being the speed. So we got to speed up, cruise for a bit, slow down, stop for a bit, speed up, cruise for a bit, slow down, stop for a bit. The derivative, the speed, has to go up and down, up and down, up and down, and has to be 0 every so often. The one that fits that description is this one here, 2. So this one goes with description A right there. Description B, a car is entering a freeway and setting the cruise control. Okay, so it's entering the freeway, setting the cruise control. As it's entering, it's got to be speeding up, and then it sets the cruise control, goes at a steady speed. Once again, the derivative is effectively the speed. What graph goes up and then stays steady for a while? That's this graph right here. So graph 1 is choice B. That leaves, of course, graph 3 to be choice C, but why? A car is in heavy traffic conditions on a freeway. Lots of traffic, it's not going very fast. The scales here are the same, so the speed is not very high. That's definitely indicated by this graph. It's heavy conditions, in other words, rush hour, you might say. There's lots of stop and go, or at least go and slow down a lot. Okay, that is what you see in this graph. This graph goes up and down and has low values, very jagged, with lots of bumps here. There's lots of speeding up and slowing down. That's what this graph is showing you, and that is choice C. Problem number 3 is a purely graphical problem, no formulas. We're trying to graph the derivative f prime of x, so you see it right up here, of the function f of x given in this graph below. So we don't have a formula, we can't do the limit definition, we need to think about slopes of tangent lines, and to try to get them as good as possible, I'd recommend using some sort of straight edge, a ruler here, to help us along the way. So we want to mark tangent lines, draw them as accurately as we can, and then estimate slopes. The first tangent lines to look for are any tangent lines that are horizontal. You can just eyeball that. Right about here and right about here, it looks like the tangent line would be horizontal. The slope of the tangent line in those two cases would be 0, meaning since the derivative gives you slopes of tangent lines, the value of the derivative as a function would be 0. So the graph of the derivative at those values of x, say right about here and right about here, the graph of the derivative is going to be 0 there. Okay? It's going to be positive in value over here and over here, where the slopes of tangent lines are positive. The derivative is going to be negative in value in here, where slopes of tangent lines are negative. But we want to be a little bit more careful now. So if we want to be more careful, we should use our straight edge and try to draw decent tangent lines. And the purpose of using the straight edges is to be able to estimate the slope a bit more accurately by thinking even about rise over run here. You know, you can spend a lot of time on this kind of problem and try to do a really super careful job. I'm not going to try to spend too much time on it because that will just bore you. But you want to get the basic idea and draw decent tangent lines here. And then estimate their slopes by, again, estimating rise over run. I think I'll just do the rise over run idea, just say for one of these. And then I'll just estimate it for the other ones here. So let's see, which one should we do the rise over run for? How about this one here? So let's continue this one a bit further. So assuming I've drawn that fairly accurately, I can think about its rise over its run. I purposely went to this next vertical line here so that the run would be 1. What's delta y over delta x here? Change in y over change in x. Change in y goes from about 0 up to a value of about 1.6. That's the change in y. And x is increasing from 0 to 1. That's about 1.6. So the value of the derivative when x is 0, at this point right here, that's where the tangent line is being drawn, is about 1.6. I could plot that point. Okay? That's the idea. I don't want to bore you and do that for every line here, but that is the idea. Let's just sort of eyeball it for the other ones here. For this one here, when x is close to negative 0.6 or so, what is the slope of that? As x increases by 0.6 or so, how much does this increase by? Oh, maybe about from negative 1.6 to about 0.8 or so. That would be an increase of about 2.4. 2.4 divided by 0.6, that would be close to 4. So right about there, the value of the derivative is going to be close to 4. I'll go ahead and just plot it at 4, just assuming that's right. It may not be. In here, the values are certainly negative. Like what's the slope of this one right there? Here, x is increasing from about 1.4 to 2, an increase of 0.6, and y goes down from negative 1/2 to negative 1.2 or so, negative 0.7 or so for the decrease in y. So it sounds like the derivative is going to be slightly less than negative 1, maybe right around here or so. And this does look like a cubic. Is it a cubic? It actually is, but it doesn't have to be. Just because it looks like a cubic doesn't mean it is a cubic. And that would mean its derivative, if you know about derivatives, are quadratics, second degree, and the graph of the derivative would have to be a parabola. And that technically means the vertex of the parabola is going to be halfway between the intercepts here at about 0.4 and 2.3 or something like that. Maybe about 1.3, 1.4, somewhere in there, which is pretty close to where I've drawn it here. Where is the slope of the black graph most negative? Right around where I've drawn it there is where it's most negative. And this parabola or parabola-like graph would have symmetry about a vertical axis through the vertex. And so it's going to go up to a value of 4 or so when you are about, how far would it be? 1.4 plus 0.6, about 2 units to the right of 1.4, which would bring us to 3.4 or so, is going to be about when the value is up to 4 or so. So that graph is a halfway decent graph of the derivative of f. Problem 4 ends up being somewhat similar to problem number 3, except we have a particular function in mind here, f of x equals natural log of x. And we have parts. Part A says use technology to estimate the values of the derivative here, f prime of 0.5, f prime of 1, and f prime of 2. In general, f prime of x, as we saw in the very first problem in this video, is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And we can approximate this with technology by plugging in a value of h close to 0 but not equal to 0. I could write this is approximately f of x plus h minus f of x all divided by h when h is small, when h is close to 0, but not equal to 0 because I don't want to divide by 0. And for this function, that'll be ln of x plus h minus ln of x divided by h. Okay, so in the first case, f prime of 0.5, let's go ahead and use h equals to 0.001 in all three cases, say. F prime of 0.5 is going to be approximately, here x is 0.5 is playing the role of x, so we have, looking here, ln of 0.5 plus 0.001 minus ln of 0.5, all divided by 0.001. Use your calculator here. ln of 0.501 is this. Don't worry about the fact that it's negative. Minus ln of 0.5 turns out to be a small positive number. These are both negative. This is slightly bigger than this, giving us a small positive number there. Divide by 0.001, you get about 1.998, and I wonder if we should round this to 2. Is the derivative exactly 2? It does turn out to be exactly 2, though this is no proof. F prime of 1 will be approximately ln of 1.001 minus ln of 1, all divided by 0.001. ln of 1 is 0, so this is a number slightly bigger than 0, divided by another number slightly bigger than 0. This rounds to 0.001. This is scientific notation here, 9.995 times 10 to the negative 4. It's very close to 0.001. Oops. Sorry about that. Divide by 0.001, we're going to get a number close to 1. Close enough to 1, 0.9995. 0.9995, that maybe the true value actually is 1, and that is actually correct. And then finally, f prime of 2 is going to be approximately ln of 2.001 minus ln of 2 divided by 0.001. ln of 2.001 is there, minus ln of 2, divide by 0.001. It's close to 0.5. How about that? 0.4998. Very close to 0.5 is the true derivative value. Exactly 0.5. It does turn out to be that. Okay, so we've approximated those derivatives. That'll help us make our graphs for part B. In the coordinate system, the graph paper that you see here, sketch the graph of f of x, and then use that graph in addition to part A to sketch the graph of f prime of x. So we want to sketch the graph of f of x equals natural log of x first. Let's do that in green. ln of 1 is 0. I can plot that point. ln of e is about 2.71828, is 1. E would be right around here. ln of e squared would be 2. What is e squared? E squared is about 7.4. When x is about 7.4, right about there, the output of the function is exactly 2. Technically, it's only exactly 2 at e squared. When x is e to the negative 1 power, 1 over e, 1 divided by e, which is about 0.37, ln of e to the negative 1 power is negative 1. So when the input is about 0.37, the output's about negative 1. 1 over e squared, or in other words, e to the negative 2 power, is about 0.135. When that is the value of x, the output of the ln is negative 2. The y-axis is a vertical asymptote here. The graph approaches it as x approaches 0 from the right. So here is an approximation to the graph of ln of x. F of x equals ln of x. Use this graph plus the data I gathered in part A to graph the derivative. I'll do that in red here. F prime of 0.5 was close enough to 2 to say it's exactly 2, perhaps. That would be the slope of the tangent line to the green graph right at that point. F prime of 1 is assuming to be 1 or very, very close. F prime of 2 is 1/2. I can connect those points with a smooth continuous curve. That would give you a good approximation to the graph of f prime. Thinking about the slopes of the natural log seem to be going to infinity here as x approaches 0 from the right, just like the outputs of its derivative then must be approaching infinity. Both functions have a vertical asymptote at x equals 0, the y-axis. And as x increases, as you move to the right, the slope of the green graph keeps getting smaller and smaller, though still positive. It's concave down with always a positive slope. The slope seems to be heading towards 0, so the value of the derivative has to head towards 0. That's the graph of f prime of x. Now maybe you know what f prime is. Maybe you could even guess it if you didn't know beforehand. It does turn out to be something simple. 1 over x, amazingly. It's kind of interesting. ln of x, which is log base e, has a derivative that doesn't involve e. It's a very simple derivative. If we did some other log base 10 of x, would its derivative be similarly simple? No, it's more complicated. This is a big part of the reason why e is such a special number. This is kind of mysterious, okay? We'll eventually get to seeing why this happens. Thanks for watching.